Now, I want to bring up something else that's very important. It gets a very small section of section, actually, it's only part of section 4 of your book, which is one of the smallest sections for this chapter. And yet, it's a very important concept, and that is the thought about where this energy is actually being stored in a capacitor. So we got a capacitor here, parallel plate capacitor, because that's our easiest kind of capacitor to talk about. And so we got positive charge up here, we got negative charge down, so we got an electric field here. So where is that energy? Well, what's in the capacitor? We got these charges. Well, it takes work to put the charges in there, but if you look inside the capacitor, what is in there? Electric field. So the energy is in some way being stored in the electric field. So that means if you had an electric field somewhere, you could, in principle, extract energy from that electric field. When I was an undergraduate, I built a crystal radio project, and as a lab project. It's really interesting because what you do is there's no electricity that runs your radio. You're simply just using electricity from the electric fields of the passing radio waves to power your radio. And so it's a very interesting sort of thing is that all these electric fields that are out there have actually energy in them. And so what we want to do is talk about how the energy is stored in the electric field. And it turns out that we talk about the energy density. So the energy density, and the symbol we use for energy density, and I hate this, is a lowercase u. Now don't confuse that with a capital U. Capital U is the potential energy. The lowercase u is the energy density. Okay, so we want to find the energy density because we already know the energy stored. The energy stored in that capacitor is 1/2 CV squared. So that's the energy stored in the capacitor. I want to know what's the energy density in that electric field right there. Okay. Well, energy density, what is energy density? That's going to be U, the total energy divided by, and I hate this too, volume. So that is volume, not voltage. And I know this, I sympathize with you. I know you're groaning right now about this. We got capital U, got lowercase u, got two V's. Okay, I didn't come up with all this. I mean, I'm using the same notation the book does, and that's just kind of annoying. All right, so what's the volume inside of our capacitor? Well, it's going to be area times the separation. So the volume, it's going to be area times D. Okay. So the energy density is going to be equal to 1/2 CV squared divided by A times D. Okay. Well, the C for a parallel plate capacitor is epsilon naught A over D. V squared over A D. Okay. So this comes out to be 1/2 times epsilon naught V squared, where that's now voltage, over D squared. But wait a minute. We know that the voltage is going to be the electric field times D. So that means that V over D is the electric field strength. So that means that V squared over D squared is going to be E squared. So that means we could rewrite this and say this is 1/2 epsilon naught E squared. Okay. So the energy density in the electric field is 1/2 epsilon naught E squared. Okay, so 1/2 constant, okay, epsilon naught permittivity constant, so we know that. E, that's the strength of the electric field. So if you have an electric field somewhere and you can measure the strength of the field, this equation is going to give you the density of energy in that region of space. So space itself would be holding energy. Now this actually turns out to be an interesting problem, because that means if you accidentally get a static charge somewhere and you get an electric field, you can actually have energy just stored in space. And that's actually a problem that they have sometimes with grain elevators, because grain, particularly powdered grain, flour, is actually very, very flammable. You get grain dust, and now you got air and a whole bunch of surface area to burn. If it burns, it can burn very rapidly and explode. There have been numerous cases of grain elevators exploding. And so the problem is, if you're not careful, because blowing all the grain around, you get triboelectrification. That is this frictional charging, so you get electric charge. And if the grain elevator has a metal framework to it, you create a big capacitor and you get electric charge in there. And so if the electric field actually gets big enough, then it can start making electric current flow through there. You get a spark, and that spark then releases all that stored energy. All that stored energy can create a giant explosion. And as I said, you can actually search, do a Google search and find about grain elevator explosions, and they can be huge and very deadly. And so modern grain elevators are designed to minimize that possibility. But it has to do with how energy is stored in the electric field. Later on this semester, we're going to be talking about fields again, electromagnetic fields, and how energy is stored in electric and magnetic fields. And then light, which is electromagnetic fields. We can find the energy of light by measuring the electric field of light.